in the laws of thermodynamics, which may be expressed in the following simple terms. After me, the first law of thermodynamics. Heat is work and work is heat.
Heat is work and work is heat.
Very good. The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you far better not.
You can try it if you like, but you far better not.
Cause the cold in the cooler will get hotter as a ruler.
Cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
Cause the hotter body's heat will pass to the cooler. Heat is work and work is heat and work is heat and heat is work.
Heat will pass.
Okay, did you get that, folks? There's all of the definitions we need, right? Just listen to Flanders and Swan. This is pretty hilarious. You should look this up. I rather enjoyed listening to this recording, okay? So that's Flanders and Swan. You can YouTube that first and second law. So this is pretty cute to listen to this whole thing. Okay, let's get that out of there. Okay, so as you can tell, we're starting the first law of thermodynamics, all right? And this is going to be a pretty massive section. You can see that I'm intending this to spread out over both weeks 3 and 4, okay? So that means we'll have 2 quizzes spanning this content, and I'll communicate with you how that's going to be spread out over the few weeks. Okay, so to get started, a few definitions. Hopefully this is mostly review. Work, a force acting over a distance, right? Work, we know, is force acting over a distance, okay? So energy, that's the capacity to do work, okay? And then heat is the transfer of energy between a system and its surroundings, okay? So we often think of heat as a thing, but it's not a thing. It is a process, okay? So heat is a process, not a thing, okay? And so those processes can be categorized into 2 different categories. So there's exothermic and endothermic, right? And so we can define exothermic as a process that releases heat to the surroundings, okay? And this is implied that we're talking about the system giving heat to the surroundings, okay? And in an endothermic process, that's a process that acquires heat from the surroundings. And so I'm going to use common definitions for system and surroundings, SYS, and it is acquiring heat from the surroundings, SURR, where I'm going to use those 2 abbreviations to indicate system and surroundings, okay? Great, so moving along, okay? So let's talk about some more definitions. Open, closed, and isolated, okay? So when we have an open system, that means both mass and energy are free to be exchanged, okay? And remember, when we say energy, we're talking about the capacity to do work. So by being able to exchange energy, we could exchange heat, we could exchange work, or both, okay? So in an open system, mass and energy are freely exchanged between system and surroundings, okay? In a closed system, we can exchange energy between system and surroundings, but not mass, okay? So the mass in our closed system is fixed or constant, okay? And so then, as you might guess, in an isolated system, we can't exchange mass or energy between system and surroundings. So it's totally isolated, okay? So rarely do we have isolated systems in chemistry. It's really, really hard to make a truly isolated system. Even if we design a Dewar, right, or a thermos or some kind of insulated device, they're still not perfectly isolated, okay? So almost all the time in chemistry, we deal with open or closed systems. And that's mostly because it's virtually impossible to make a truly isolated system. We can try our best, and in lab, you're going to hear me say in lab a lot, and I know that's kind of sad because who knows if we'll actually be in lab next semester, but all the same, in the lab, we can try our best to make isolated systems, but usually they are not perfectly isolated. Okay, so moving on. So now here's a little activity for discussion, okay? So for the following 4 situations, so that's, 1, 2, 3, 4, what happens to the temperature inside each box in the due course of the process? Is the box in thermal equilibrium? Where does heat flow, surroundings to system or vice versa? And so what these processes, what they're describing is here, okay, so 1 and 2 are a diathermic container, where 1 is an endothermic process occurring in a diathermic container, and 2 is an exothermic process occurring in a diathermic container, excuse me. And as you might guess, processes 3 and 4 are both in adiabatic containers, and they're endo and exo. So pause the video and see if you can kind of work through this, see if you can guess, is the box in thermal equilibrium? Where does the heat flow? What happens to the temperature inside the box, okay? So go ahead and pause and see if you can think through this for just a moment. I'm gonna just continue right along and do it, okay? So, and all these boxes are the system, right? So the surroundings is out here and the system is inside the box, okay? So as it turns out, the diathermic container is always going to be in thermal equilibrium with its surroundings and system, okay? It's always going to be in thermal equilibrium. And in an endothermic process, because the system has to acquire heat from the surroundings, okay, this is the direction in which heat will flow, okay? And so if we wait long enough, it is in thermal equilibrium with its surroundings. So if the surroundings are 298 K, the system will be 298 K if we wait a long enough period of time, okay? And as you might guess, in an exothermic process, the system will deliver heat to the surroundings in a diathermic container, because remember, diathermic means it is thermally conducting, okay? And so this system is definitely in thermal equilibrium with its surroundings as well, okay? So if we wait long enough, in the diathermic container will be the same temperature as the surroundings, okay? Maybe not as soon as we initiate the process, right? Whether it be endothermic or exothermic, but if we wait long enough, it will be in thermal equilibrium. Okay, what about the adiabatic container where there's an endothermic process? So remember, adiabatic means it's thermally insulating, okay? And if we had, like, let's say maybe a perfect adiabatic container, it could create an isolated system for us, okay? So this will not be in thermal equilibrium, okay? It will be a different temperature than the surroundings. And so now, will it be hotter or colder than the surroundings? And if it's an endothermic process, it has to acquire heat from somewhere. So the only place it can acquire heat from is itself. And thus, it will become colder, okay, than what it was initially. And similarly, all adiabatic containers are not in thermal equilibrium with their surroundings, okay? And this exothermic process, it wants to deliver heat It can't deliver heat anywhere else but to itself. So this will make the system hotter. Okay? So this is starting pretty basic from here, but now we have to start kind of thinking about how heat is going to be exchanged between system and surrounding. And if you recall from our very first week and from that cute little song I just played for you, right? Heat flows from a hot object to a cold object, not the other way around, okay? Remember that. Okay, so let's get into internal energy, okay? So we are going to use the letter U for internal energy. Okay, so I know I used a bunch of different letters for energy previously. In the thermal world, U is the internal energy, okay? And so remember this delta, right? This delta gives me final minus initial, but also don't forget about state functions, right? So state functions are always represented by capital letters, always. And a state function is path independent, okay? So that means we only care about the final state and the initial state. We don't care about what happened in between. And there's this rather cute picture I like to draw of the USA. So suppose you're here, like maybe somewhere in Colorado, beautiful mountains and forests and trees and stuff, okay? And you get on a plane and you want to travel to Chicago, okay? Well, as viewed by a state function, you know, Denver would be somewhere around here, right? At like, 1 mile above sea level. And, here's Chicago, a bunch of awesome buildings, formerly the tallest building in the world, Sears Tower. Navy Pier with the Ferris wheel. That's right, that's a Ferris wheel. Bunch of brick houses with chimneys. Yay. Okay, so this is Chicago, Chi-Town. Okay, so suppose now we take several different paths. You want to travel between Denver and Chicago, right? And suppose you just drive there directly. So you take this path A, okay, where here's your initial state and here's your final state. Great, okay? Suppose now instead of driving, you take an airplane, okay? So you get an airplane and you go, and then you land at O'Hare. Fantastic, okay, initial and final. So you still made it to the same place, whether you drove or you fly. Suppose you're feeling really crazy and you want to go on a round the trip world. So this is like going all the way around the world. Okay? And you still end up in Chicago. If your change in elevation between Denver and Chicago is a state function, then it does not matter which path you took. Okay? So if we think of, let's say, like our internal energy initially and our internal energy finally, notice in this state function, there's nothing that says what path we took. Now, undoubtedly, if we were talking about the work that we did, all of these paths would have very different amounts of work done, okay? And so I'll back up for just a second and show you, look, work, lowercase w, not a state function. Energy, big capital U, state function. Also, look at this, heat, lowercase q, not a state function. Okay, so let's write that down. Heat is a path function. Energy is a state function. Work is also, like heat, a path function. Okay? So, capital letters get capital letters get state functions, and often when we can simply just say the change, right, in internal energy, then we know that we're dealing with a state function if we only care about the final minus the initial, okay? And so if we just look at energy in terms of joules, so that's the intensive parameter, but if we look at molar internal energy, UM, which is U divided by N, that's going to be our extensive parameter. And we'll often see this molar internal energy because that gives us one less parameter to deal with, right? We can reduce our variable space by just absorbing the number of moles into that term, okay? Great, so let's keep moving on. Okay, so now let's kind of starting to get into the meat of internal energy. And you're gonna often hear me say molecular properties versus bulk properties, okay? So I'll read this to you. The manifestation of bulk properties, and by bulk properties, that could be heat capacity, density, all of these things that you'll also hear me call physical observables, okay? Physical observables. We could even call it chemical observables in the case of it being a bulk chemical property, such as oxidation state, all right? All of these bulk properties, these physical observables, all stem from molecular properties. And those molecular properties being the way a molecule can vibrate, the way it can rotate, its molecular structure, right, the connectivity of atoms. So all of these bulk properties, all of our physical properties, stem from the molecular properties, okay? So the first example of that is the internal energy of a simple monatomic gas, all right? Which here I have that equation written for you right here, okay? Delta M as a function, or excuse me, change in molar internal energy, UM as a function of T, is equal to UM 0, so there's this constant here where when T is equal to 0, we still have some amount of internal energy. That's called the ZPE, the 0 point energy. So even at 0 Kelvin, there is still an interaction between electrons and protons, and that gives us some base 0 point energy, okay? Plus 3/2 RT. Okay, where did this 3/2 RT come from? Well, recall from our first week in fundamentals, if I think about this noble gas, so suppose something like helium, okay? Helium is free to translate in the X, Y, or Z dimension. I'm gonna start referring to these now as the degrees of freedom. And so that doesn't just have to refer to the translations, okay? The rotations, the vibrations, even the electronic transitions. I'm gonna call these degrees of freedom. Sometimes I write that DOF, degrees of freedom. Okay, those are the things the molecule can do. And where does this 3/2 RT come from? Well, recall, for each degree, we get 1/2 RT or 1/2 K Boltzmann T, depending on if we're talking about a mole or a molecule. So thus, we can say the internal energy of a monatomic gas, okay, monatomic gas, or a noble gas, if you will, okay, is 3/2 RT, and of course, plus some very tiny contribution due to the ZPE, the 0 point energy, okay? So let's see here. And so now finally this discussion of thermal motion, so the disorderly motion of molecules as a result of heat transfer, that is a bulk manifestation of molecular properties, this disorderly motion. And so the idea here is, if we think of this in exo versus endo, so like in an exothermic process, for example, a molecule is transferring heat to other molecules. Well, what does that mean? What it really means is it's transferring degrees of freedom, right? The energy is stored in its own degrees of freedom. And so thus, when it transfers heat from system to surroundings, it is expunging some of that energy stored in its degrees of freedom. And of course, the molecules in the surroundings are going to then absorb that energy into its degrees of freedom, okay? And so, as you might guess, the more degrees of freedom a molecule has, the more places energy can be stored. Okay? So when we start talking about thermal motion, this disorderly motion, we want to think of this as, the rotations, the vibrations, the translations, all of the things the molecule can do, and how and where that energy is going to be stored. Is it stored in the translation? Is it stored in the rotation? And of course, equipartition tells us there's 1/2 RT just for each of these terms. So there's 1/2 RT for a rotation, 1/2 RT for a vibration, 1/2 RT for a translation, etc. Okay? So moving on. So here's an activity. Here's another thing to come up with. Come up with expressions for the internal energy of a representative monatomic gas, linear molecule, and nonlinear molecule. And then how does the internal energy of a nonlinear molecule compare to that of a monoatomic gas? Well, I already did the monatomic gas for you, right? That was in the previous slide. Um as a function of T equals um0, the 0-point energy, plus 3/2 RT, okay? Monoatomic. Okay, so what about a linear molecule? Well, it's still going to have this as a function of 0, but how many degrees of freedom is it going to have? Okay, I have a cheater note coming up. So here's a representative linear molecule, okay, something like carbon dioxide, right? So CO2 has 2 axes of rotation, okay? You can rotate around this way, which would be these molecules flipping end over end, right? Or it can rotate this way, which would be these molecules rotating to this axis, end over end. So it can kind of go like this, or it can go like this. So that gives us 2 additional degrees of freedom to the already 3 degrees of freedom it has from translation. So it can move in the XYZ dimension, but it can also rotate in 2 free dimensions. And even if we looked at something like nitrogen, N2, which I know it won't have an IR spectrum because it's just doesn't have a dipole, right? If we're talking about N and N. It doesn't have a vibrational spectrum. It doesn't have a rotational spectrum, but it doesn't matter. It still has an axis of rotation. It can rotate around that axis, or it can rotate around that axis, okay? If it rotates around that internuclear axis, right here, if I draw a line through the internuclear axis, that doesn't count because it just looks like an atom spinning on end, okay? So I'm going to X that out. Hopefully that's understandable. And so now that gives us 5 degrees of freedom for a linear molecule. 3 are translations, 2 are rotations. Why not any for the vibrations? Because there's not enough energy at room temperature to stimulate a vibration, okay? So now, of course, outside of that range of temperature, then we might see additional degrees of freedom. But for our normal, I'm going to say, I'll say representative room temperature. Representative room temp expressions. And by representative, I mean room temperature like maybe plus or minus 50 or 100 degrees or something like that. We're going to dive into this in much more detail. You know, at what temperature does this start to fail, okay? But for our normal, like representative room temperature, monatomic gas has 3 degrees of freedom, thus 3/2 RT. Linear gas has 5 degrees of freedom, thus 5/2 RT. And then what about a nonlinear? Well, you probably saw from that picture, let me zoom ahead here, okay? Look, a molecule like water will have 3 rotational degrees of freedom because now when it spins on that axis, because it's nonlinear, it doesn't look like a barrel, you know, like a single molecule rotating around. This nonlinear molecule makes all 3 of these rotational axes unique or different, okay? So you can see the expressions 3RT. Where does 3RT come from? Well, there's 3 degrees of translational freedom plus 1, 2, 3 degrees of rotational freedom. That makes 6 half RT for nonlinear, which is the same as 3RT. Okay? So now the question was, how does the energy of a nonlinear molecule compare to that of a monatomic gas? It's twofold, right? 3 halves versus 3. So there's 2 times that energy. So what we could say is 2 times the energy must be supplied to a nonlinear molecule to get the same rise in temperature. And that's because if we're starting to transfer heat, right? Go back to that exothermic, endothermic, right? If I am transferring, transferring energy from, system to surroundings, the nonlinear molecule has more degrees of freedom in which that thermal energy can be dumped into, okay? So we have to supply those degrees of freedom with heat to get a rise in temperature, all right? And we'll see the manifestation this has on heat capacity as we move through these slides, all right? Okay, so 5 half RT for a linear molecule, 3 RT for a nonlinear molecule, and of course, 3 half, sorry, that's a little sloppy, 3 half RT for a simple atom, okay? Okay, so moving on. So let's dive into the first law of thermodynamics. All right, so the first law of thermodynamics says, don't talk about thermodynamics. No, I'm just kidding. That was a little Fight Club humor. Okay, the first law of thermodynamics says the internal energy of an isolated system is constant. Okay, well, that cute little song I played for you, right? Another thing you could say about the first law of thermodynamics, the internal energy is equal to the work plus the heat, okay? It's as simple as that, okay? And so you can see I've written it in 2 ways, and I want you to get used to seeing the first law in 2 different ways. Delta U equals W plus Q, or du equals dQ plus dW, okay? So this is for measurable changes. And by measurable changes, I mean what we can actually accomplish in the lab, right? Because that's final minus initial. If I can measure simply put, if I can measure the temperature of something from its initial state to its final state, then I can measure what its accompanying change in energy must be. Okay? So what does this thing mean? Well, this is, assuming I can spell, infinitesimally small changes. Okay? And so when we're talking about infinitesimally small changes, we're kind of saying use calculus. Okay? So this is the type of relationship we're going to be able to use to exploit other relationships. When we go down the rabbit hole of deriving equations and physical relationships and, right, connecting bulk properties to molecular properties, we want to use the expression of U for infinitesimally small changes. Okay? And so now we arrive at our first definition for work, and I'm going to give the very correct definition for infinitesimally small changes, not for measurable changes, but for infinitesimally small, okay? dW, by definition, is negative F times dz, okay? A force acting over a distance, all right? So the unit of force is Newton. The unit of dz is meter. So a Newton meter is a kilogram. A Newton is a kilogram meter per second squared times another meter gives me a kilogram meter squared per second squared, which is a joule. Okay. And so there are several other, so this is the definition of work that I want you to kind of start thinking of, all right? There's a couple other definitions of work that I'll just use as examples. One of those is actually surface tension. And so you might be used to the definition of surface tension that says the resistance a liquid has to spread its area, okay? Well, another definition of that is the work required to bring a molecule across an interface, right? So if you think about like some interface, okay, and by interface, I mean like liquid on this side of the line and gas on this side of the line. If I try to bring a molecule across that interface or the other way from liquid to gas, there's work required. I have to apply work over some distance to make that happen, okay? And that's related to surface tension. And so I could write surface tension is dW, still work, infinitesimally small changes, but now this by definition is sigma times dA, okay? Where sigma is my actual surface tension, and that has units of Newton per meter, okay? And then of course dA would be my change in area. That's related to that definition, the resistance of a liquid to spread its area. And so we know that that is meters squared. So when you multiply that by meters squared, you get a Newton meter, and we recognize that a Newton meter is a joule, okay? Another definition of work that we rarely think about, but electrical potential. That's work, okay? The work required to move an electron through a potential barrier. Think about it. When you're doing chemistry, you're doing work. You're putting electrons into new orbitals, right? You're making new chemical bonds. That is a force acting over a distance, right? There's some force that's required to penetrate that electric potential from the orbital, and that electron has to move over a distance, okay? We could also just think of it simply as moving an electron through a wire, right? So think even bigger. So when I talked about that chemical reaction, right, that'd be molecular, but think about a bulk property. A bulk property would be just literally plugging in my cell phone charger, for example, and the electrons flowing through that wire. Well, they have to have a force acting over a distance to make that happen. So we could say the electrical potential, the work due to electrical potential, is often given as phi times dq, okay, where this phi is going to be my potential in volts, right? That's my potential voltage. And this dq is a change in charge, okay? Which is given as a coulomb, right? And so if you take a volt times a coulomb, you get a joule, all right? So we're mostly gonna be playing with this definition here, okay? Basing it off of the true, like, the simple root force over a distance. But I just wanted to draw these two examples. Surface tension and electrical potential are both examples of thermodynamic work, okay? So moving along, so I'm gonna stop the lecture here. So there's a lot of stuff. You can see I have a lot of slides. So I'm gonna do a larger number of shorter videos in this module than a shorter number of larger videos, if that makes sense. Okay, anyways, I'm gonna cut it off from here. I'll see you on the next video, folks.